Welcome. In part 1 of chapter 6, we covered gases, liquids, and solids and the intermolecular forces that connect them. In part 2 of chapter 6, we will cover the gas laws. Here we have a quick review from last chapter. A solution is a homogeneous mixture of two or more substances. These substances include a solute, which is a substance that's being dispersed throughout the solution, and the solvent, which is the substance doing the dissolving, and this is usually present in the greatest quantity. When a solution exists, the intermolecular forces between the molecules in the solution are constantly occurring. The solute molecules are interacting with the solvent molecules and with each other. The solvent molecules are also interacting with each other. Solutions form most readily when the intermolecular forces between the solute and the solvent have the most overlap. This leads to a like dissolves like situation where the solutes and solvents with similar molecular structure are going to interact more readily through their intermolecular forces and form a solution. We can see here a few examples. The first is oil and gasoline. Both of these are very nonpolar molecules. Neither of them are capable of hydrogen bonding, but they're able to interact through their London dispersion forces. These will form one layer. The next example that we have is oil and vinegar. Oil is composed of mostly nonpolar molecules, where vinegar is composed of water and acetic acid, both of which are capable of hydrogen bonding and are very polar molecules. This will form two different layers. The top layer, the oil layer, will have the lower density, and the vinegar layer, the bottom layer, will have a higher density. Ionic substances are able to dissolve in water as well. An ionic substance undergoes ionic bonds, which are the strongest intermolecular force, but they're also able to go through dipole ion interactions. In this case, the dipole exists on the water molecule. We can see the oxygen has a partial negative charge and the hydrogen has a partial positive charge. This means that the partially negative oxygen is able to interact with the positively charged ion. And so over time, the salt molecule, or the ionic substance, will be able to dissolve into solution because each of the water molecules will make an ionic dipole interaction with a positive charge, and then the partial positive part of the hydrogen on the water molecules will interact with the negative. This is called solvation. Next, we will change gears and discuss the laws that govern the interactions and properties of gases. Before we can start talking about the mathematical basis of these laws, let's go through a few postulates that are assumed for these laws to occur. The first postulate is that the particles of a gas are in rapid constant motion. We already discussed that this is a universal truth for atoms, that the bonds between atoms are constantly vibrating and moving, and this postulate also states that the particles of a gas are in rapid motion. The second postulate is that the particles of a gas are tiny compared to the distance between them. Overall, the gas is going to take up a fairly large volume, and this will minimize the number of collisions. There is very little attraction between the particles of the gas, and that the collisions that do occur between the gas molecules are going to be perfectly elastic. And then our final postulate is that the temperature is a measure of the average kinetic energy of the gas molecule. Depending on how quickly these gas molecules are moving, how much energy is stored in them, that's going to be relative to the temperature. Now we're going to relate how the pressure, the volume, the temperature, and the number of molecules that are present are all interrelated. The first law that we'll look at for this relationship is Boyle's law. Boyle's law relates volume to pressure. and is assuming that the temperature is held constant. We can look at the equation that on the left side of the equation we have the initial state, and on the right side of the equation we have the final state. In the initial state, it says that the initial volume times the initial pressure is going to be equal to the final volume or times the final pressure. Or that in general, the volume is inversely proportional to the pressure. We can use this schematic to help visualize the math behind this equation. At constant temperature, the volume of a gas is going to be inversely proportionate to the temperature. So, if a set of molecules takes up this area at 4 atmospheres of pressure, and we reduce the pressure to 2 atmospheres, the molecules of the gas will take up double the volume. If we decrease the pressure again to 1 atmosphere, we will once again double the volume. According to Charles' law, we're now going to hold the pressure constant and look at the relationship between the temperature and the volume of the gas. The relationship in this case is going to be directly proportional between the volume and temperature. That means the initial volume divided by the initial temperature is going to be equal to the final volume divided by the final temperature. Since this relationship is directly proportional, we can use a linear line to map out the increase in temperature over time. Here on the x-axis we have temperature, and on the y-axis we have volume. If we increase the temperature, we'll see a proportional increase in a linear fashion of the volume. Another example of this involves a gas inside of a balloon. If we're to take a balloon, the gas is going to occupy a certain volume of that balloon. If we cool the balloon down, for example with liquid nitrogen, then the gas will condense and occupy a smaller volume of the balloon. In order to make the discussion of these gas laws a little bit easier and universal, the concept of standard temperature and pressure has been developed. These are a standard temperature of 0 degrees Celsius, a standard pressure of 1 atmosphere, which is what we're generally experiencing on Earth. What we do know about standard temperature and pressure is that if we have 1 mole, or 6.02 times 10 to the 23rd molecules of any gas at standard temperature and pressure, it's going to occupy a volume of 22.4 liters, which is roughly the size of a basketball. Now, interestingly enough, this applies to all different types of gas. All different molecules will occupy 22.4 liters at standard temperature and pressure. Because of this relationship, we can derive the ideal gas law. Before we derive the ideal gas law, we can combine Boyle's and Charles' law into the combined gas laws. What this means is that if we change any one of these variables in a system, the other variables will be affected. When we combine this with the number of moles that are present, we end up with this equation that says the pressure times the volume is equal to the N, which is the number of moles, times R, a constant, times the temperature. If we have any three of these 4 variables, we can calculate the fourth. The R is just a constant, so our R that we're going to use for the scope of this course is going to be 0.0821. Now it's important for us to look at the units of R. In this case, our R value is in liters, that means the volume has to be in liters, times atmospheres, that means the pressure has to be in atmospheres, divided by moles, that means that N has to be in moles, so instead of grams or molecules, it has to be converted to moles, and then finally that our temperature has to be in Kelvin. Any attempt to utilize this equation in order to solve for one of these variables means that we first must make sure all of our information has the correct units.